All right, good morning, everybody. Today we're going to talk about section 3 of chapter 13, arc lengths in space. Remember, just recall what arc length is. If we have a curve, the arc length of a curve is the distance from one point, from point P to point Q on a curve. That's the arc length, S. That's what we're going to look at here. We're going to look at we'll examine the shape of the twists and turns of a curve in three-dimensional space. So this is only in 2 dimensions. So think about if we had a helix. So the arc length would be as if starting from this point, going on to this point, it would be this. Because not only is it rotating clockwise or counterclockwise, it's also increasing in altitude because it's going up on the z-axis. And that adds a new dimension to it. So the first thing we're going to look at are arc length along a space curve. We're going to look at only looking at smooth curves. In space or on a plane. We need to find the measure of the length of the smooth curve. Remember, smooth curve means it's differentiable on the domain D. What we're going to look at here is we're going to look at examine points along the curve by giving their what we call directed distance. No, it has to be along the curve. From a starting point, or let's call it the base point, we actually did this earlier in the last section where we talked about the curves and planes. So let's define this. The length of a smooth curve given by the parametric equation of J and C of TK. So the length of a smooth curve, R equals x, y, z as functions of t, where t is between, say t is inside a bounded interval. T is between some a and b. As t increases. From t equals a to t equals b. So we define it as the length is the bounded interval from a to b, since it's a closed curve, of the magnitude of the velocity vector with respect to all those. Remember, for the velocity is the first derivative of the position vector, and the length of this arc from point A to point B is the integral of the magnitude of that, which means since L means it's the square root of x prime at t squared. I we're doing with magnitude, plus y prime at t squared plus z prime at t squared dt. What this tells us is we're calculating the curve in 3D space from any standard parametrization that agrees with any conditions stated, or any initial conditions or any limitations. So we know that this tells us that the length of a velocity vector v, which is dr dt, enables us to write the formula for the length of an arc. Oops. So we look at either way. So this is what we call the arc length. So basically all we have to do is find the derivative of the position vector and then do the integration from point A to point B. Let's look at an example here. The glider is soaring upwards along the helix. RT equals cosine T of I sine T of J plus T of K. How long is the glider's path from T equals 0? So this is A to B. So the first thing we have to do, so it's looking for the length, so we're looking for this. So we have to find the derivative. We have to first find V. Derivative of cosine is negative sine. Derivative of sine is cosine. And derivative of t is 1. Now we have to find the magnitude. Negative sine t squared cosine t squared plus 1 squared. So our length goes from 0 to 2 pi. It's 1 complete revolution. Let's rewrite this. So we have the negative squared makes positive, so we have sine squared t plus cosine squared t plus 1. As an identity, sine squared plus cosine squared is 1. So we have 1 plus 1. So we have the square root of 2 dt. The integral of the square root of 2 is square root of 2t from 0 to 2 pi, which says our length, since t is 0, 0, so we have 2 pi square root of 2. That's the length of our motion of this glider. Basically, all it's saying is here's our x, that's our y. So we're starting from t equals 0. So we see our initial point. This is our initial point is 1, 0, 0. So we start at 1. As we rotate, it's going circular, but it's also going up because of this component. So what this says is, as we go all the way around to where we begin, this is 2 pi. we just measured that arc length. All right. I say instead of starting at 0, if we choose another base point, at t equals 0. On the smooth curve, C. We can parametricize the curve C by t for each value of t in the closed interval which determines the point P of t equals x of t, y of t, c of t. As a point on C and has a directed distance of the integral as from the initial t to our final t. No, I say this is not, that's not t, it's Greek tau, because t is our bounds. We're looking at time, initial time to final time. So we're using tau. You'd be very careful, because it's very easy to go a little bit further and get those mixed up. So we're integrating with respect to tau. S of t so it's measured along C, starting from its base point, t sub 0, to the end. Now, about S of t, if our t's increase in size, so it goes from t sub 0 to t, we'll say that S of t is the distance along the curve C from point t sub 0 to point T. If we go the opposite direction, we say that S of t is the negative of the distance. So it all depends on how we're integrating. If we're going from t sub 0 to t, and which we found out from calculus 1, that if you integrate from a to b as opposed to b to a, the only thing different will be the sign in front of the answer, not the answer itself. So it's simply going to be the negative of the distance. All right, so each value or each point of S determines a point along our curve C and the parametrization of C with respect to T. So what we're looking at each point along the way as T goes from T sub 0 to T, or from T to T sub 0. We're looking at each point separately. All right. Because of that, because it measures or determines each point and we can measure it, S is called an arc length parameter. With a smooth curve C. Right. So that's next thing we got to look at is what's the difference between what we just talked about there originally we started some T sub 0 and go from there. Now we can start at any point P and move from there. That's all that's saying. So in here, some P at some point is S of T at the integral of T sub 0 to T of our magnitude of the velocity with respect to some value tau. So that's what this is saying. So the arc length parameter with some base at some other point along the curve. If R of T is defined in terms of some parameter value of T and S of T is the arc length, Then we could say solving for t as a function of s will give us some given function t of s. So the time parameter is a function of our arc length parameter. That happens then the curve C can be parametrized in terms of S by replacing T in our function. Remember, what we used to have was R of T, but now since T is a function of S, we now have that parametrization. This new form identifies a point on the curve C with its directed distance along the curve. From P T sub 0. So this new form identifies a point on curve on C with its directed distance along the curve. So remember, S is our directed distance. All right, let's look at an example here, what that means. Find the arc length parameter along the helix from T sub 0 to T. So we know that arc length parameter is this function. And we found out earlier, remember when we took negative sine t squared cosine t squared plus 1 squared, which is exactly what this can give us. We find the derivative. So we have to find that, in which we did that, and we got square root of 2. But we can't use t, we have to use tau. So our velocity then became radical 2 t, because we took it from 0 to t. Okay, so we have to solve for t. So we know s is equal to radical 2t. That means t is equal to, or s over radical 2. Which this is now t is a function of s. So once we found the value, we know that s is equal to, so what do we do with that? Substitute t into r. This will give us the position vector of arc length of an arc length that is parametrized. So we're looking for r of t, since t is a function of s. R of t was originally cosine of t. Sine of t, j, and t. So now anywhere we see a t, we put ts. So that's t is s over radical 2. Sine s over radical 2. And then s over radical 2. So we just, everywhere, once we solve for t, we just replace t with what we just had. Since we found the arc length and since we found the velocity, well, we really looked at the speed of a vector on, or a particle on, a smooth curve. So once we find the velocity, the speed is the magnitude of that velocity. So the derivative of s with respect to t is the magnitude of your velocity at t. What does this do? This tells us that the speed of a particle moving along a path is the magnitude of V along T. All right. Even though our base point, p sub 0, helps determine S, our arc length, equation it plays no role in our reparametrization. When we went the function within a function, our compound functions. The rate that a point moves along the curve C is independent of its distance from the base point, p sub 0. Why is that? Is because it's all it does is find us the distance at a certain point, and there is no determination of the rate. It's just a location, it's a scalar type positioning. Since we have a smooth curve, or it's differentiable, our magnitude of V is never 0. Because it's differentiable, our derivative of S is always positive. We could say it's an increasing function, but again, it all depends on the direction of integration. The unit tangent vector. Okay, from last section, we know that the velocity vector v is the derivative of r is tangent to the curve C that the vector which would take the vector tangent to the curve T is equal to that position, which we've seen before. Again, we've seen this, we've done this, we did directions, looking at moving objects. We had the speed times direction. The speed was the magnitude, and the direction. So we know that the tangent, the unit tangent vector is that. T is differentiable. Which means it's continuous. We know that because V is differentiable and continuous. And C is a smooth curve, which again means that it is differentiable and continuous. Based on the condition, as long as T is differentiable. I'm sorry, V of T. So what does this mean in our graph? We have our X, our Y, our Z. So we have, let's look back at our hang glider. So R starts at the origin and goes to a point. The tangent vector T is that equation. So this is R. R is our parametric equation we start off originally. So that's what it's saying. It's tangent to it. And when we say tangent to it, it's also perpendicular to it. Now let's look at an example. Find the unit tangent vector of the curve R of t, representing the path of the glider we had earlier. So we're looking for the unit tangent vector. So we're looking for this. We need to find v, and v is the derivative. So v of t equals derivative of 1 is 0, 3 cosine is negative 3 sine t I. 3 sine, derivative of sine is cosine, and derivative of t squared is 2t. Now we've got to find a magnitude. Negative 3 sine t squared, 3 cosine t squared, plus 2 squared. Negative 3 squared is 9 sine squared t. 3 squared is 9 cosine squared t plus 4. No, t squared. It's 2t. These two have 9, so we can factor those out. So we have sine squared t plus cosine squared t plus 4t squared. Sine squared cosine squared is 1. So that is our magnitude. So our unit vector negative 3 sine t over that I, 3 cosine t over the radical j, nine plus 4t squared k. So there's our unit vector. Yeah, it's already a unit vector. Because it's the unit tangent vector, and basically what we're looking at here, we can compare our position vector r and our velocity vector. And what we found with that, and we can see that r dot v, if it's 0, it's perpendicular or orthogonal. So what that says is, let's look at a unit circle. Any point along the way, the unit tangent vector is touching the point 1 point, so automatically it's orthogonal. and it moves in a counterclockwise direction. We see that the it is the change of position. With respect to time. So we see that already because it's a derivative of it. So what can we ask? There are two questions that are very important. How does the position vector change with respect to the arc length? And second, what is the derivative dr ds? So how does the position vector change with respect to the arc length? What we see here is the arc length is, in essence, a position vector in itself. So as the position vector changes, the arc length changes. So as time changes the values of each point along the path, it changes its position with respect to the arc length. What is the derivative of dr ds? Well, let's take what's ds? Because remember, s is a function of t, so ds dt is differentiable, it's continuous, so it's always positive. Because it's a continuous function, it's differentiable, that means therefore it has an inverse. So which we could find is the inverse is this. So the inverse of ds dt is dt ds, which is really 1 over ds dt, which is 1 over the magnitude of v. This makes r differentiable. As a function of s. So dr ds, we know we've discussed r of t. We've also discussed that t as a function of s. So dr ds, dr, and t is a function of s. So dr dt is the velocity vector, and dt ds is what we just calculated. Which is the unit tangent vector. So the unit tangent vector is actually dr ds. All right, that's it for this section.